well as risk analysis. Moving forward, we're going to use the simulated models to perform also a stochastic optimization, and then wrap up with the future work. And so just to give an overview of what we are considering here, we are dealing with one copper deposit, one mine. Now we are evaluating the potential of the open pit mine here. We have somewhat of a few destinations. We have one waste dump and one ore processor, and we designed two stockpiles where we selected some medium and low grade stockpile. We predefined it, which a minimum and a maximum grade that could feed those stockpiles in order to try to help the optimizer with blending these grades and feed the material. So material can flow from the pit directly to the processor or to the stockpiles and so on. Something that is interesting here is that both metallurgical recovery and the quality of the products are depending on the simulated copper grades, but also of other elements such as sulfur and iron content. But these ones we haven't had the opportunity to simulate, so we are using the estimated value stability. But this is something that we wanted to expand for future work. So just to show some aspects of the ore body model. So we're dealing with a copper deposit, which is highly controlled by some veins, I would say. And in the left-hand side here, we have, so this is a plan view. So this is one section of the deposit, and we can see the smoothing effect, like the visual aspects of how the grades are smoothly vary from one location to another throughout these chains. And on the right-hand side, we have the simulated like 3 realizations, and we can see much more variability and uncertainty throughout these different realizations. So another visualization here, we can see how the deposit dips in. So this is now a cross section, and you can see that the mineralization goes along this strike here, and the estimated model has present a very strong smoothing aspect, whereas the simulations maybe do not connect that much the material or show higher grades and lower grades, where instead of this elongated. So what we also compared here was the difference, the grade tonnage curves. So I separated the graphs into 2 just to be able to zoom in a little bit into different parts of the graphs to highlight the range of uncertainty provided by the different curves. And all the results are presented here will be in a percentage related to the deterministic of a certain target. So in this case here, we see that for low cutoff grades, the estimated model, as we've seen over and over, overestimated the amount of tonnages. And we have a breaking point more or less like here. And for higher grades, we see that it underestimates the amount of tonnages present in the deposit. Regarding the grades above the average grade above the cutoff grade, you see that the estimated model consistently underestimates these grades. Why I'm focusing this is because we observed something interesting as well. So with this, for this deposit, we were the deterministic optimization we're only able to select blocks classified as measure indicated and inferred for optimizing the value chain. And but even though like we have the previous performance was considering the whole ore body. But if we remove then what was classified as potential, so we only look at what's measured, indicate, and infer, we have something slightly different. So before the breakpoint was around this part of the graph, so now we can see that there is some stretch, which means here that the smoothing effect was not linear, and not considering some parts enlarge this difference in the smoothing effect. So now the amount of this breaking point here between the underestimation and overestimation of ore tonnages is now further at a higher rate. And so this is something we observed. So we generated simulated realizations for the whole mineralization, and then we use just what was flagged as measured, indicated, and inferred for using traditional techniques. So the same blocks for both optimization. So that's what I was highlighting before. So before doing this filtering, the breaking point was around here, where you wouldn't have much of an over and lower estimation, underestimation. So now we then took the estimated ore body model and for a traditional optimization. So here's a result where extraction period varies from blue early periods to red later down the road. And consider standard steps, ultimate bit definition, pushbacks, instruction sequence, and stockpiling optimization. And here are some of the results we observed. So the deterministic optimization decided for a very, I would say, aggressive extraction in the early periods, where some of the material were stockpiled in 3 different stockpiles, very low, medium grade, and high grade. Very low, and medium grade. And these would then use to feed the mill afterwards. And with respect to the mine tonnage, yeah, so that's it's extracted at full capacity at this 100% over almost 8 years, and then that consistently slows down. So you could use material from the stockpiles. And so this is how material is fed into the mill from which destination. So in the early years, we are mostly providing material directly from the mine, but as of year 12, we start using the medium grade stockpiles, and finally end up using the low grade stockpiles. And there's a little bit of more material coming from in the final this. But that's pretty much the strategy. But what we also saw, so we took the schedule that we received from the deterministic approach, and we fixed decisions. So this block is going to this destination and so on. But what we evaluated afterwards, there was some misclassification given the kind of grade strategy. And so here I combined the results of both the mill and the stockpiles, and there is a misclassification at around 30% of the mill started. This percentage here is related to a target of the mill. And we have a combined misclassification of 30%, considering both mill already and stockpiles. The mill itself, material will go, there is around 20% misclassification. So material maybe slowly below cutoff, or could be a bit more. This will have a huge impact on cash flow assessment down the road. So the optimizer forecast says that would produce 80% more copper than was actually observed by the simulations. And in terms of NPV, this would go down to 30% overestimation of NPV. So now we look at this as like, yeah, okay, so how can we improve this production schedule? So we then use the set of simulations and input this into the software. For this case, we are using the KPI Cosmos software, and we're able to come up with the following solution. So I'm just comparing here the schedule. So in the right hand side you have the stochastic, and the left hand side have the deterministic schedule. So we can see physical the instruction sequence has changed. We still have some sort of resemblance, so such as these two pits here, so satellite pits here, and the pits over there. But when to extract material has changed, and for instance, this part here is only considered for mining in the later periods, but this one is a bit early, and we decided that in this area we save for later. And this is a cross section. We see sync rate and smoothing on screens are working. We have, of course, more deviations in later periods because of how the software works. Deviations in early periods cost more in terms of the objective function than later on. And now going to the production forecast and comparing with what we find out from the deterministic optimization. So in the green lines here, we have the result of the stochastic optimization. So in this case, I forgot to mention, we only simulating copper grades. We are not simulating boundaries or high grades and low grades. We're not simulating other elements, just copper. So that's why we don't see risk analysis over tonnage itself. And what we were able to obtain was a slightly different strategy. So we are not as aggressive in the first 9 years, maybe 10 years. So there is almost 20% less material being mined in this the beginning. And we end up resulting in a 2% smaller pit overall. And also the strategy to the stockpiles was we decided to use much less the stockpile, and only one of them. So we were sending material to the low-grade stockpile for the first 7 years, whereas the deterministic used much more. So this is the red curve here is whatever was initially planned for the stockpiles. So we're reducing the movement in the early stages. Regarding the processing plant input, we're able to fill the mill at full capacity over almost 16 years, so 15, and we have a lower throughput at a less period, with the ranges within acceptable, with the minimum and the maximum over acceptable. So we were able to feed the processing plant at. So what I wanted to highlight here is that before we saw like a good amount of misclassification going to the mill. So we initially thought of maybe you would be interested to investigate a project that would take a lower capacity for the mill, but we're able to fill the mill's full capacity for almost 16 years. And regarding copper produced, we were able to obtain almost 3.6% more copper than the risk analysis of the deterministic model. That's still below what was initially forecasted by the conventional forecast. However, if you look at the NPV, we are able to catch up providing a little bit higher than the deterministic optimization, the forecast. But regarding the risk analysis of the traditional optimization, we were able to find 35%. So we regained all the NPV that the deterministic model didn't account for. So that's pretty much the set of results that I had to share. So with conclusions in this study, so this is an ongoing study, so we're still evaluating more and more aspects. And but with this, we saw a large overestimation of tonnages above the project's cutoff grade. A lot of misclassifications going on, especially the early years that would harm the NPV assessment. And the deterministic, there's also a drawback of the deterministic approach is that optimizes things in silos, so it doesn't consider the synergies of optimizing different components simultaneously. The project's becoming aware of the risk already in the early stages, so this information gonna go forward. And we were able to achieve the production targets that we initially thought, okay, maybe we have as this amount of material that we initially thought. We were able to improve NPV by 35% compared to the risk analysis of it. So for future work, we wanted to investigate opportunities for improvements, such as different processing plants capacity, maybe to slow down and have a longer life of mine, see how all this behaves. There's also studies for possibility of investigating synergies with the nearby projects, and maybe combine the material feeding the mill from sources and from different areas. And also we are interested in optimizing the mining complex, considering blocks beyond what was considered as a measure indicated and inferred by traditional approaches to see if this would reveal potentials for improvements, and then guide maybe next drilling plan, and possibly obtain increase the resource reserves for the future. And one thing that we also interested in is in simulating the ore boundaries, because the mineralization seems to be highly controlled by these channels, as well as also considering other elements, because the processing plant is also dependent on iron contents and so forth as well. So that's what I have for today. Thank you very much.